At this point, before we continue going down the periodic table and looking at electron configurations of elements, I want to highlight something that is important, right? We have mentioned that N determines the energy of our orbitals, and so we expect as N gets bigger, as N increases, the energy increases, and so we fill the lowest energy orbitals first. On the left here, what I have is a plot of energy of orbitals. Hopefully you can read this if you're not watching this on too small of a screen. Energy of the orbitals versus their designation. So we have 1s orbitals down here, and they're our very lowest energy orbitals, and they're a lot lower energy than everything else. As n increases, though, the different values of L get closer and closer in terms of their orbital energy. So this is the order we've been filling things up to now. With hydrogen, we started hydrogen and helium. We started with 1s. As we went down to the next row of the periodic table, we started filling the 2s orbitals and then the 2p orbitals. And then we go 3s and 3p. So for the same reason we did 2s and 2p, s is a little bit lower energy than p, and these are both 3. But when we get to 3d, because there are L equals 2 orbitals with n equals 3, our 3d orbitals, we can see they're actually not the next set of orbitals. The 4s orbitals actually come first, and then the 3d, and then the 4p. And we can see this pattern repeats with the 4s and 5s. After we fill up the 4p orbital, it's actually the 5s orbital that's the next lowest energy, then the 4d, then the 5p, and then we get to the next shell, and then it goes, and then things get even a little bit more crazy. Now we can actually see this reflected in the periodic table. So I'm going to go back to our view of the periodic table, and in the way that the elements are filled up here. Now I've got helium here is behind my head, but you just imagine it there. I guess I can scroll down for a little bit. There we go. So we're filling in our 1s orbitals up here with our 2 electrons going to hydrogen and helium. Our next 2 electrons are the s electrons in lithium and beryllium, so those are our 2s electrons. And then we're filling in the p orbitals. That's our 6 2p electrons. That's filling up boron through neon. Once we get to neon, all of those orbitals are full. When we go to the next row of the periodic table, we're starting to fill the n equals 3 shell. And we fill in the 3s and the 3p. So similar to 2s. So 2 electrons in the s orbitals represent sodium and then magnesium. That fills up the s orbital. Then we move on to the 3p orbitals. Aluminum, silicon, phosphorus, sulfur, chlorine. And then when we get to argon, all of the 3p electrons are filled. And then we don't immediately go to the d electrons. We instead fill in the s electrons for the 4s electrons. So potassium and calcium have electrons in the 4s orbital, but then we start filling the 3d orbitals. Now there are 5 3d orbitals. We can put 2 electrons in each orbital, so there are a total of 10 electrons that can go into d orbitals. So our 3d orbitals are our transition metals here, going from atomic number 21 out to 30. These are filling into our 3d orbitals. So the 4s gets filled first, then the 3d, because that's then the next energy up, and then finally we fill in the 4p electrons over here on the right side of the periodic table. And the same thing repeats for 5. We get 5s, 4d, 5p. All right, so just wanted to link that back to what we can see with the periodic table there. So what that means is if we pick an electron, an element, let's say scandium here, scandium, which has 21 electrons, as we just saw, we're going to use the noble gas configuration. We're going to say, okay, well, everything up to argon, we can say we already know how that fills in. So we can say the electron configuration is going to be the same as argon, which, just to be clear, means we filled up our 1s orbitals, our 2s orbitals, our 2p orbitals. We fill up our 3s orbitals and our 3p orbitals. That's what this represents. So when we write argon, it means this, that we have all of those orbitals already filled up. So that is, let's count them, 2 1s electrons, 2 2s electrons, 6 2. All right, so we've got 2 plus 2 plus 6 plus 2 plus another 6. If we add all that up, we get 4, 10. That's 18 of our electrons. We have 3 more electrons that need to go into scandium. So they're going to go, again, following the order of our orbitals that we have in this diagram over here. Let me point at the correct orbital. We fill in the 4s electrons next. So we write these as 4s2 and then an electron in 3d in one of our 3d orbitals. Or if we write this with our little boxes that we've had, we have our spin up and spin down into 4s, and now we have 5 3d orbitals, 2, 3, 4, 5, and we get 1 electron in one of those orbitals. Okay, so that was a bit of a long-winded explanation, but that explains as we get to lower and lower rows of the periodic table, these energy orderings matter, but you can look at the periodic table to sort of remember that energy ordering. Now, I wrote it as 4s2 3d1. We technically should write this as argon for scandium 3d1 4s2. We'll write whatever is our lowest n will come first. I'm not going to be too picky about this. If you write it the other way around, it's fine. But what this can help you remember is that actually, if we lose electrons, they actually come out of these lower n orbitals first. We're going to talk about that as we proceed through the chapter, but just something else to bring up. Okay, so that's the basic idea. We fill in the electrons in the order that they're filled in the order of the energy. We put 2 electrons per orbital. If we have multiple electrons, we spread them out into the different orbitals first, and within the same subshell, like the 3d orbitals or the 2p or whatever, according to Hund's rule. And that's how we can figure out our electron configurations. So in the next video, we'll go through an example of something further down the periodic table using these principles, figuring out what the electron configuration is, kind of like we did here with scandium, but a little bit more complicated example.